Hello and welcome to helpyourmath.com. This is part 2 of sketching absolute value functions. If you need to watch part 1, I do go into a little more detail. Right here, I'm just going to jump right into examples. For each of the following functions, we're going to name the parent function f of x for each of the given functions. Then we're going to describe the sequence of transformations that got us from the parent function to the given function g of x. And then we're going to sketch the graph of g of x. So first of all, this is an absolute value function. That's what it said in the title, and that's what this is. So our parent function is f of x is equal to the absolute value of x. Next, we want to describe the sequence of transformations. And remember, there's 3 things that we look for. First, is there a reflection? And the answer is no. We would know there was a reflection because there would be a negative coefficient, and that's a positive, so no reflection. Next, we're going to look for vertical and horizontal shifts. There would be a horizontal shift if there was something happening within there besides just the x, so there's no horizontal, but there is a vertical shift. Because we have a -4 here, that indicates to us that there is a vertical shift where we're shifting this down 4 units. And the last thing that we look for is a stretch or a shrink. Because the coefficient a is equal to 3, that indicates to us there is a vertical stretch by 3. So that means we're going to take that graph. Normally we would go over 1, up 1. This is going to pull the graph up and make it look a little bit skinnier than our parent function. And if we get caught up, you can always fall back on a table of values. So always know that table of values do work. I do suggest being smart about the table of values. First, identify what the vertex is before you do any table of values or really even start the absolute value graph. So let's use this information to figure out what the vertex of this graph is. Sorry, that looks terrible. I'm gonna try it again. So the vertex should be at the parent function would be at 0, 0. Since there was no horizontal shift, we're still going to be have an x coordinate of 0. The y coordinate down 4 units means we're shifting this graph down 4 units. It would now be at -4. So it's going to start at 0, -4. And then what this vertical stretch is going to do is normally we would go up 1 over 1, but this vertical stretch means we're going to go up 3, 1, 2, 3. And then over 1 in either direction, up 1, 2, 3. And if you don't really like this, up 1, 2, 3, over 1, up 1, 2, 3, over 1. If this is kind of weird for you, which I totally get, make that table of values. So when we make our table of values, put the vertex in the middle. We're going to create 5 coordinates here, or 5 ordered pairs. We're going to put the vertex in the middle, 0, -4. And remember that all of the other points, all the other inputs are symmetric about the vertex. So we're going to go 1 unit to the left of 0 at -1, 1 unit to the right. 2 units to the left of 0, 2 units to the right. And -1 and 1 will have the same output. -2 and 2 will have the same output because that's the beauty of the symmetry of our absolute value functions. So I only need to plug in 1 or -1. I'll plug in -1. This would be, so I'm going to say g of -1 is equal to 3 times the absolute value of -1 minus 4. The absolute value of -1 is 1, 3 times 1 is 3, and 3 minus 4 is -1. So I had -1, -1. We can see that point there. That also means it would be 1, -1, which we can see I put that point there. Now just to verify these other 2, if I plug in 2, g of 2 would be 3 times the absolute value of 2 minus 4. The absolute value of 2 is 2. 3 times 2 is 6, and 6 minus 4 is 2. So it's 2, 2, and -2, 2. Is that what I have? 2, 2, -2, 2. So there we have it. Connect those with a nice, smooth, straight edge. And we can see that nice V shape, right? It's absolute value, so we should see a V shape. And that would be our vertical stretch. In our last example, it looks like we have a little bit of everything. So first, let's name the parent function. That's going to be f of x is equal to the absolute value of x. Next, we want to identify all the different types of transformations. So first, what I notice is that we do have a negative here. That indicates that we do have a reflection about the x-axis. So whereas the parent function would open up, the negative graph will open down. The next thing I want to identify are the horizontal and vertical shifts. So to figure out those, we focus on what's being added or subtracted within the function and what's being added or subtracted outside the function. Inside the function, we have x minus 1, so that indicates to me that h is equal to 1. Outside the function, we have plus 5. That indicates that k is equal to 5. H being 1 means that we are shifting this graph 1 unit to the right. K being 5 means we are shifting this graph up 5 units. And then from there, we could figure out the vertex, which I'll write down here. So the vertex, remember the vertex of the parent function would be at 0, 0. But this tells me I'm going to add 1 to 0 for the x-coordinate, add 5 to 0 for the y-coordinate, giving me a vertex of 1, 5. The last thing that I haven't used yet is this 1/2. This 1/2 indicates to me that we have a vertical shrink by 1/2, vertical shrink by 1/2. Now, I know that when we have vertical shrinks and stretches, it can be scary. I'm going to start by not creating a table of values, and then I'll go back and create the table of values, because always know you can fall back on those. To start, I'm going to start with the vertex 1, 5, so that's going to be up here. And then I'm going to use the other information. So the fact that it's a reflection means normally for the absolute value, I would go up and over, but this tells me I'm going to go down and over. The other thing I need to take into account when I find more points is that we do have this vertical shrink by 1/2. So basically what that tells me is that I'm going to go down 1 unit and over 2 units. Down 1 unit over 2. I can do that again, down 1 over 2, down 1 over 2. If I wanted to, I could do that again and again, but really it's key to have 5 points. Having 7 is great, 9, fine, but 5 is basically the minimum you want for an absolute value function. Now, if you're like, wait a minute, where did those points just come from? Let's make our table of values. So our table of values, we're going to choose 5 points, and the middle point is going to be the vertex. So we have this one, vertex, and these two. The vertex is 1, 5, and with this one, I do want to be very particular about the x values that I choose. Because the coefficient is 1/2, I want to make sure that what's inside the absolute value ends up being even, so that way when I take half of it, I still end up with an integer. So normally I would go 1 to the left and 1 to the right of the vertex, but that's going to end up being fractions for me. So instead of going 1, I'm going to go 2 over. So here I am at 1. If I go 2 to the left, that puts me at -1, and 2 to the right will put me at +3. Then I want to do that again. I'm going to go 2 further. 2 more will put me at -3, and 2 more to the right will put me at +5. Now the reason that I want to go the same distance is because as long as they're the same distance around that x-coordinate of the vertex, they're going to have the same output values. So -1 and 3 are both 2 units away from 1. -3 and 5 are both 4 units away from 1. Now I only need to plug in one of those pairs. So that's the beauty of the symmetry of this graph. If I plug in 3, g of 3, that would be -1/2 times the absolute value of 3 minus 1 plus 5. Working inside the absolute value, 3 minus 1 is 2. The absolute value of 2 is 2. And then we have -1/2 times 2. That's negative times positive is negative. And half of 2 is 1, so -1 plus 5 is +4. So I know that 3 will map to 4. I also know due to the symmetry that -1 will map to 4. And again, it's not wrong. If you chose to use 0 and 2, you'll just end up with fractions, and that's not a problem at all. Okay, but lastly, we're going to use either -3 or 5. I'm going to go with 5. So g of 5, that would be -1/2 times the absolute value of 5 minus 1 plus 5. 5 minus 1 is 4. The absolute value of 4 is 4. Now negative times positive is negative, and half of 4 is 2, so that's going to be -2 plus 5, which is +3. So we get 5, 3, and -3, 3. Is that what I had here? 5, 1, 2, 3. There it is. -3, 1, 2, 3. So that's what our graph will look like with all of those transformations, which was a lot. So I know this is a lot to take in, but always, always, always fall back on the table if needed. These have been examples of looking at transformed absolute value functions. Thank you for stopping.